Hello Internet, today we're going to be looking at force-directed graphs in Unity. So a force-directed graph is a graph, a series of connected nodes that have forces applied to them. So nodes that are connected will pull towards one another, and nodes that are not will repel one another. So effectively, it will try to group things that are related and push everything else away. And so theoretically, this will kind of give us a nice three-dimensional graph, I hope. So that's what we're going to try to get to. Not in this video. In this video, we're just going to kind of introduce it and do some really basic stuff. And then I'm going to finish reading the papers and stuff that I'm doing to actually catch up on this. And then we'll actually implement the actual algorithms. But hopefully, I know enough that we can actually implement this in a way where we get it working. So I have this force-directed graph here. It is nothing. There's nothing here. So we're going to just create a graph. And I'll add that on. There's, again, nothing here. And so what I want to do... Actually, this makes the most sense. So we're going to have nodes and edges. So every single... Do we need the edges? No. Well, no. Sorry about that. No, we don't. So I can just create a node. Yeah, a node works. A node of type T content. Let's stay away from generics, actually. This is Unity. They don't like it when we use generics. So we have a node. This node is going to have a position. So vector 3 of our position. And then it's also going to have a list of children. I don't know if I like children for a graph, but that'll work for this. And so this node knows itself and it knows everybody else. So, do we also want incoming nodes? I don't think so. We might though. I haven't figured this out yet, but this should be enough to get us started at least. The code is going to be super scrappy because we're just trying to get this working, which is why these are just public fields instead of doing anything intelligent there. So what we need is a list of nodes. So let's create that. And that'll just be our nodes. So we have a node array effectively that has all of our nodes. What we want to do is apply some sort of force so that they will come towards one another if they're connected. If this directed graph has a child, it will apply a force towards and pull the other one towards it. If it doesn't, it will push it away. So I'm trying to think of how we're going to iterate over all of these nodes to only find the ones with children. Nodes except. So we could use this except thing, which is going to pull out a certain set of nodes. I'm pretty sure that'll be really slow though. So I don't know if we want that, but we can experiment with that. I'm also going to give it a velocity. We're not going to edit the position, we're going to edit the velocity. Making this up on the spot. We'll see how this goes. So, since we have a velocity now, I can do for each node in our nodes. Let's grab the node and say its position plus equals the velocity, or the node's velocity rather. And we'll multiply that by the time delta. So now we have things that will move. Assuming the velocity is not 0, this will move, which is good. We don't have any way of drawing these yet. So I think, I don't know if I like this, but we're going to use gizmos for now. I mean, obviously there's nothing to draw here, but I don't want to use meshes because we're going to get rid of meshes in this later on. I'll talk about that later, or if I get some extra time. But I don't want to use meshes for this. And then if we do, there'll be one mesh for the entire thing. So this is going to be our node in our nodes again. And we want to draw them. So let's do gizmos color equals red. The hard part is going to be we aren't going to know what's connected to what. Actually, we will. Ha! We can do this. Gizmos dot draw wire sphere at our node position, and we want them to have, say, radius of 0.125. So they'll be 1/4 of a meter wide. That should draw the spheres. So we have all of our nodes drawn, but if I want to actually draw dot color, sorry about that. If we want to draw the actual lines, we can actually just iterate over every connected node in our node's children. And so now we have the node and we have the child node. And so I can just do a gizmos draw line from our node position to the connected nodes position. And so now we have not only just nodes, but we also have what's connected. So we should be able to actually see that, hopefully. Then, just because this is a really rough project, we are going to generate some nodes. So for int I equals 0, I is less than, do I want to do 100? Let's do 20 nodes for now. So we'll generate 20 nodes. Nodes add I. Ooh, that's not how you do that. A new node. There we go. And so they'll all be just one after the other. And then we need to give them some children. And I don't know the best way to do this. So we're gonna make this up. I just want this to be like random children. So some of them will have children, some of them won't. It's not a problem if they don't, I don't think. Well, it shouldn't be. And so we just need random children from the nodes. So nodes dot where? This should work. So we want to take nodes where the node has a random chance of 0.5. So there's a 50% chance that all the current nodes will be added to the children of this one, but it's all random. That makes sense to me. It's total randomness and total just random, but theoretically it should work. We want this to a list. There we go. And so what this is going to do, even though we're referencing the node here, we're not actually taking the node and doing anything with it. All we're doing is getting a random value and saying if that random value is greater than 0.5, the random value is between 0 and 1. So if it's greater than 0.5, then add it to this new list, and that new list is now the children. The interesting thing is we're actually using the nodes here, which means that for the first node that's generated, they can't have children because there won't be any other nodes in that list. Since it's added at the same time, there won't be anybody else. And just so we have some additional fun stuff, let's do position equals random dot inside the unit sphere. So that'll be inside a unit sphere, which means it has a 1 radius everywhere around it. And then we'll multiply that by like 10. All of this is hard-coded, that's fine. We'll get there. But this should get us drawing our actual gizmos, or it'll crash. Argument cannot be null. I think that's our velocity. So we'll set that equal to vector3.0. So there's no velocity inherent to any of these. Theoretically, at this point, we should probably have a constructor, but we've already done all of this. So we'll move on, and then we can do that later. So hopefully, nope. Oh, duh. Nodes equals a new list. We were adding to a null object. Nodes hadn't been initialized yet. This should fix that. I should have known that. Anyway, now that we have that, hopefully it's running, and we have this gross little thing, right? So this is just our graph. And you can see some of the nodes are connected to things. There's no way to currently tell what are incoming and outgoing things, but it will slightly matter. But this is our graph. It looks kind of gross, but it works, and we can work with this. So what I want to do now, well, actually, let's restart that. We'll get a different graph, but that should be fine. So notice that these nodes aren't all connected. So like this red node is not connected directly to this one over here. And that's what we're counting on. So we want a force to push those two nodes apart. But then the two that are connected, like you can see this one is also connected to the one on the complete other side. We want our algorithm to pull those two towards one another and actually slowly move them together so they're more concise. So that's the problem we're trying to solve here. Hopefully it works. I don't know. Never done this before. So let's apply graph force. And so we're going to create this apply graph force method. And it's going to update the velocities for everything. There's no friction here. I don't think we need friction. We might need friction. We'll see. So we have a force graph. There's two things we need to do. So for each node in our nodes, we need two lists, right? We need the children, which we already have. That's just node.children. But we also need the disconnected node, disconnected nodes. And that's going to be equal to our nodes, except the node children. So we're going to pull off all of the children that are part of this. So we have two lists that are complete opposites of one another. So one has all of the elements over on one side, and one has all the elements on the other side. And so this way, for everything, let's do node dot velocity plus equals do I want to do it this way? No, I don't. Sorry about that. Let's do, so the difficult part is there's actually two different forces we want. We want one to push away, and we want one to pull. And we want that it's not just strictly pull it all the way to our node. We want to be able to say, I want these nodes to be 1 meter apart. So if you have just two nodes and they're connected, they should pull to 1 meter within each other, and then that should be where they stay. You don't want them to just pull right on top of one another, because that doesn't work. You can't really tell what's going on there. And so let's start with that, actually. So for each variable connected node in our node.children, we want to apply a logarithmic force. And so the reason we're doing a logarithmic force is because, if I just write this out quick, the log, let's do log 10. Log is just natural log. We don't want that. So the cool thing is if I do, say, 10 divided by 10 in a log base 10, it doesn't actually matter. Any logarithm will get you to the same point. But if you have 1 in here, which is what that would get you, this results in 0, which means you get 0 force. Which means if we have distance on one side and divide that by some constant, like say the desired node distance. Let's call it the desired connected node distance. If I do this, this function becomes 0 when the distance between the nodes is equal to the desired connected node distance, which means there's no force at that connected distance. And actually, if it goes too far, it starts pushing it back away, back towards this desired connected node distance, which is perfect. That's what we want. So that's what we're going to use here. I need to actually create these. And let's make it something we can configure, because I have a feeling this is going to be, it's going to be something we want to tweak. So we have our distance. Let's make this distance equal to our node position minus the connected node's position. And that'll be the magnitude of those two vectors. And so after this, we get our distance between the two. And I want to add on just another force here. This will be our connected node force. And we have an applied force from this function. And so based on whatever this connected node force is, we can apply a force. I don't really know what else I was planning on saying there. I feel like there was something, but oh well. We have a force to apply. This is just a float though. We still need our difference, which I can actually get from here. So let's do our difference, plug it in there. We get our two node positions like that. We have our applied force and our distance. And so now that we have the applied force and the difference, we can actually apply this. So I want to say connected node dot velocity plus equals the force we're adding, which is going to be the applied force times a time delta. Because keep in mind, this is still happening repeatedly over time, so we still need that time multiplier. There's still an acceleration there. That's what we're tracking here, and that happens over time. So we have that, and then we also need the difference times, or the normalized difference, which gets us a direction. And so this way, we can actually apply a velocity in a direction, I hope. And theoretically, I should be able to stop this, let it compile, and then start it. That's neat. Now keep in mind there's some things do not apply forces. But that's cool. This must be our original node because it doesn't apply anything. I think we're getting a little bit carried away here. This isn't really what I want. It looks trippy though. Super cool. Do you remember those like Windows 98 screensavers where it would do this? I feel like we just made that on accident. Huh. That's super cool. Not really what I was going for, but we're missing some of the formula, so I have no idea if this is correct. But anyway, it's a thing, I guess. Huh. Now, getting distracted because that was interesting. Wasn't really what I was expecting, but it works. I don't know. It's cool. So let's duplicate this again, except we're going to use our disconnected nodes. Our disconnected node. Swap that out for our difference calculation. Modify the velocity we're going to apply. Everything else can stay the same except this. Instead of using a logarithm, we don't want these to be a specific thing or a specific distance away, but we do want them to push things away, and we want them to push them away more slowly the further away they get. So if something gets 10 units away, we want that to be slower than 20 units away. And I think exponential makes sense. Everything that I've said says use exponential, so we're gonna use an exponential curve. So disconnected node force times r, actually, sorry, divided by the distance the distance squared. So math f pow distance squared. And then we just need our disconnected node force, like so. And that's probably way too weak for this. It will, at this rate, it would fall off way too quickly. But it should get us at least to a starting point, and we should be able to actually start applying this. I think we're going to need to reverse the signs on one of these two, because they're probably both going to push them away, and I don't think we want that. But I think that's the is that the change I want? I don't think so. Because if the velocity was being applied in the wrong direction, they would have just kept going out or in, right? Huh. Bye. I think I evicted all of my nodes. Let's try this again. Huh. Okay. Permission to be confused. Where did everything go? Let's drop that there. Attach to Unity. See what's going on, because I'm really confused right now. Oh, not a number. That's nice. Why is that? Do we divide by like 0 or something? We might have, if we divide by 0, I'm pretty sure we get not a number. Let's throw a check in there. If the distance is equal to 0, is not equal to 0, then we'll apply this. If it is, then we'll skip it. I think that'll make sense. Obviously, whatever we did here is what introduced the error, because we didn't have the issue before adding this. So it has to be something we did here. I just don't know what. Maybe that. Disconnected node. No. Okay. Let's try this again and see where we end up. Hopefully somewhere better. Yeah, I think we just created a constantly expanding universe. Yep. Well, that wasn't really what we were going for, but and so I think we can actually, let's tune that down. If I reduce the force, it should come back in. So I was using a disconnected node force of 100, which the distance would have to be 10 for that to be low. And so I think that's probably why it expanded so much. So hopefully by bringing that back down, everything can kind of collapse again. Or if we just, what if we just increase this to like 10? Getting kind of a bit high on the force, but that's fine. I think this is getting closer to what I was trying to accomplish. It's not exactly there, and this one is still way off in the distance and still going actually. Some of them are, yeah. Okay. I think this is sort of where I want to be. I don't know if this is actually what I want it to do at all, but it's interesting enough that I'm like, okay, this is cool. I'm gonna continue reading up on how these things actually work. There are some actual like algorithms that have been designed for doing this rather than just plugging in numbers. So we'll see where that goes. I'll post some links to what these things are. If you want to explore them either in Unity or in like D3, which has native support for them, then I'll post links to those as well. But that's it for this video. I think it's an interesting place to stop. I don't know what this is, but it's a thing. That's as much as I can say about it. So yeah, we'll pick this up later. I have some ideas on how I want to use it. There's a lot of things where you can visualize graphs and kind of manipulate it. So I feel like if we can start grabbing these nodes and actually like inspecting them or manipulating them or just using it to render graph stuff in a cool like 3D way where you can actually like explore it, I think that'd be really cool. So that's sort of where I'm trying to go with this. Don't know if it's going to work. This seems to indicate that there's a giant shrug in the middle if this is going to work. So we'll see. But that's it for this video. So until next time, see you, internet.